Have you ever wondered, how global security teams manage to protect tens of thousands of computers simultaneously, like without the whole system just completely collapsing into absolute chaos?
Yeah, to pull that off, you really can't just install a standard antivirus. You need this highly automated nervous system. And today, looking at the CrowdStrike architecture, it becomes pretty clear just how deep that automation actually has to go.
I mean, when you think about managing 50,000 laptops, servers, mobile devices across, what, a dozen time zones, the logistics are just staggering.
Oh, absolutely staggering.
So today, we are opening up the hood on the CrowdStrike Falcon platform to see exactly how they execute this. Welcome to another deep dive.
Glad to be here.
We are pulling from a really massive stack of sources today. We've got official CrowdStrike certified Falcon administrator training guides, technical architecture reports, and even some real-world Reddit discussions.
Which are always fun.
Yeah, where actual security professionals are debating how they use these tools in the trenches.
Yeah, so the mission for this deep dive is to basically navigate the exact menus these teams use every day. We're getting into the host setup and management console, breaking down host groups, deployment strategies, and sensor update policies.
And then ultimately, we're going to connect those configurations to Lev Security Operations Center workflows, right? To see how this platform responds when an attack actually happens.
Exactly.
Okay, let's unpack this.
Yeah.
Because before a security team can organize their defenses or, automate any kind of response, they actually have to get their sensors onto the devices.
Right. You need visibility before you can even have security.
Exactly. And getting the Falcon sensor onto a machine across a massive enterprise is, it's a highly stealthy operation.
It has to be. For anyone managing an enterprise IT environment, the traditional deployment model is just a massive headache.
Oh, yeah.
You run an installer, it heavily taxes the CPU, and then the worst part, it forces a hard reboot before it even starts monitoring.
Which is crazy because that kind of disruption is a non-starter if you're trying to, say, install security tooling on a critical backend database. You can't just have downtime.
Right. Zero downtime is the rule. And what's fascinating here is that the Falcon sensor bypasses that entirely. It installs completely silently in the background.
No reboot requirements.
No reboot on any operating system.
Yep.
Administrators deploy it using this specific command line execution. It's typically like setup.exe silent CID, and then that's followed by this really long, unique alphanumeric string.
Ah, okay, the customer ID.
Exactly. That customer ID is the architectural anchor for the whole deployment. When you run that silent install, that ID hard codes the link between that specific machine and your organization's unique Falcon tenant in the cloud.
So it's basically the only way the newly installed sensor knows which command center to report to for its instructions.
Spot on.
So dropping this sensor into a system is like letting a highly trained guard dog into a massive corporate building.
Yeah.
You don't need to shut the elevators down and evacuate the lobby just to let the dog in, right?
Right.
It just walks through the door and immediately starts sniffing around. But there is a major catch from what the sources say. You do need to turn off the metal detector at the front door.
Yeah, that's a great analogy. And that metal detector is Deep Packet Inspection, or DPI.
Right.
A lot of corporate networks use DPI appliances to basically intercept outbound network traffic. They decrypt it, inspect the payload for, data exfiltration or malware, and then re-encrypt it before sending it out to the internet.
But the guides are very clear that deep packet inspection must be entirely bypassed for CrowdStrike's own traffic.
Completely bypassed.
If an admin leaves DPI on for the Falcon sensor, the sensor just completely breaks its connection to the cloud. Which seems counterintuitive, right? Why would a security platform inherently reject another security tool inspecting its traffic?
It really comes down to how the sensor defends its own integrity. So Falcon uses strict certificate pinning to defend against man-in-the-middle attacks.
Okay, meaning it knows exactly who it should be talking to.
Exactly. The sensor has this hard-coded cryptographic hash of exactly what the CrowdStrike Cloud's security certificate should look like. So when a DPI appliance intercepts that traffic, it's essentially acting as a localized man-in-the-middle.
Oh, I see.
Yeah, it decrypts the packet, reads it, and then re-encrypts it using the company's own internal certificate.
And the sensor looks at that new internal certificate, realizes it does not match the hard-coded CrowdStrike hash, assumes the connection is hijacked by an attacker, and just immediately severs the communication.
Boom. Which leaves the host completely unmanaged. So network admins literally have to configure their firewalls to allow CrowdStrike traffic to bypass DPI completely.
Wow. Okay, so once that tunnel is clear and the sensor is successfully deployed, the security team manages the whole fleet from a unified extended detection and response, or XDR, console.
Right. And tracking that initial deployment is handled by this specific capability, literally just called monitor deployment.
Because pushing a silent command to 10,000 remote laptops is one thing, but actually verifying it is another.
Right, you need proof. Monitor deployment gives the team a dashboard showing exactly how many hosts successfully got the sensor, how many failed, and how many are actively communicating with the console.
Now, looking at the host management UI, there's a feature that caught my eye. Administrators have this button labeled Disable Detections. It temporarily commands the sensor to stop evaluating behavior and sending alerts to the cloud. It essentially silences it.
Yeah, it does.
But wait, if clicking Disable Detections essentially turns the machine into a ghost and creates a massive blind spot, why even give admins that button?
It sounds risky, I know.
Right, like why not just force them to use a dedicated isolated test network if they need to experiment, rather than blinding a live production machine?
Well, in a perfect world, testing would always happen in a sterile lab. But if you look at those real-world Reddit discussions from SOC
Like
analysts,
CrowdStrike.
exactly. You sometimes have a proprietary legacy business application acting up in production, like maybe a custom piece of accounting software is suddenly crashing every time it tries to write to a specific memory address, and the IT team suspects the Falcon sensor is blocking it.
And moving that old legacy app to a test network might just break its dependencies entirely.
Exactly that. So they need a way to isolate the variable right there on the production floor. By hitting Disable Detections, the admin temporarily pauses the security logic just to see if the accounting software starts working again.
And if it does, they know they need to write a custom exclusion for that specific software.
Right. But the risk you pointed out is very real. If they forget to re-enable detections, that host is running without active monitoring, meaning retroactive and new detections will not populate the console until it's toggled back on.
Okay, so the guard dogs are inside the building, they're reporting back, the deployments are verified. But getting the sensor onto a machine is only half the battle, right?
Barely half.
Because once you have 10,000 active sensors flooding your XDR console, how do you prevent a generic security rule meant for, like, a marketing intern's laptop from accidentally locking up a critical back-end server?
Right. This is where we get into host groups. Because without a rigid grouping architecture, managing security at scale is just impossible. Grouping determines which policies apply to which machines.
And the platform offers 3 distinct types of host groups, right?
Yeah, to handle different logistical challenges. So the most straightforward one is the static group.
Right, and these are fully manual. An administrator actively selects specific machines and places them into the group. You'd use a static group when you absolutely cannot risk a machine's policy changing automatically.
Exactly. Think of an organization's primary domain controllers or root certificate authorities. You do not want a domain controller accidentally inheriting a looser security policy just because of some automated tagging error.
That would be a bad day. But manually dragging and dropping 10,000 daily active machines into groups is obviously not feasible.
No. Nobody has time for that. This is why the vast majority of an enterprise fleet is managed through dynamic groups. They automatically add and remove hosts based on real-time evaluations using the Falcon query language, or FQL.
Yeah, looking at the FQL syntax in the training guides, an admin could write a rule for a dynamic group that says ostock windows anti-tag dot production.
Right, and the mechanics of how that tag gets there is crucial. During that initial silent installation we talked about, the admin can inject a grouping tag directly into the command line string.
Okay.
So when the sensor boots up, it reads its local registry, sees that production tag, and phones into the cloud. The cloud evaluates the FQL logic and instantly drops that machine into the production group.
Applying all the associated security policies immediately.
Instantly.
And if an IT tech later, say, re-images that machine for a new user and changes its provisioning tag to testing, the next time that sensor checks in, the cloud reevaluates the FQL, pulls it out of production, and drops it into the testing group.
Yep, zero human intervention required.
That is incredibly smooth. And for organizations with heavy API usage, there's a third option called static by ID.
Yes, because host names can be duplicated or, changed by local users, which breaks automation scripts relying on those names. Static by ID manages hosts strictly by their unique agent IDs, or AIDs.
Providing a stable, unchanging identifier for external automation tools.
Exactly.
But here's where it gets really interesting. With all these dynamic rules constantly evaluating tags and operating systems, a single user's device could easily qualify for multiple groups.
Right.
Well, very easily. If I have a dynamic group for all Windows machines, another for the finance department, and another for machines in the London office, a single finance manager's laptop in London is suddenly sitting in 3 different groups at the exact same time.
That's a very common scenario.
But if the London group disables USB drives and the finance group allows them, doesn't that create a massive, chaotic tug of war for which policy actually applies?
It would create absolute chaos, yeah, if the system didn't enforce a strict policy precedence hierarchy. The platform actually resolves these overlaps mathematically.
Mathematically. How so?
Every single policy an administrator creates must be assigned a precedence number. When a host finds itself in multiple groups with conflicting policies, the Falcon Cloud looks at the precedence rankings. The policy with the lowest number, meaning the highest precedence, always wins the tiebreaker.
Oh, okay. So it forces the security team to explicitly rank their priorities. If the general Windows baseline policy is set to precedence 100, but the stricter London Office policy is set to precedence 10, the London USB restrictions will override the baseline because 10 is mathematically lower than 100.
You've got it. That precedence model is what allows an organization to layer policies safely. You build broad, forgiving policies at the bottom with high precedence numbers and highly targeted, restrictive policies at the top with low numbers.
Which naturally brings us to the policies themselves. So we put our critical servers into a strict static group and our laptops into dynamic groups. But that creates a new problem.
Patching.
Exactly. When CrowdStrike releases a massive new sensor update, pushing it blindly to every single group simultaneously could be disastrous.
Oh, yeah. Pushing an update to 10,000 machines at once isn't patching. That's essentially a self-inflicted denial of service attack if the update contains a bug.
Right. So how do you patch the security software without potentially breaking the company's entire infrastructure?
Well, you have to stagger the rollout, and the sensor update policy is designed to automate that staggering. The platform gives you several deployment tiers. The most aggressive is Auto Latest, or N.
Meaning machines in this tier download and install the new sensor version the exact moment it reaches general availability.
Right. But the architecture guides heavily advise against putting your entire fleet on Auto Latest. Instead, they really emphasize Auto N1 and Auto N2. Auto N1 keeps the assigned hosts exactly one version behind the newest release. Auto N2 keeps them 2 versions behind.
It's like letting someone else taste the soup first to make sure it's not too hot.
That's a perfect way to look at it. Think of the Auto Latest tier as the crumple zone on a car. You assign your IT department's internal laptops or a subset of non-critical workstations to Auto Latest. They absorb the impact of the update first.
So if there is a rare bug that conflicts with your specific corporate software environment, those Auto Latest machines will catch it.
Exactly. And by the time that update trickles down to the Auto N1 tier, which houses your standard employee fleet, you already know it's stable.
And I noticed for environments that absolutely prioritize stability above all else, like critical medical equipment or industrial control systems, there are long-term support or LTS sensor versions that rarely change.
Yes, for when you absolutely cannot risk any disruption. But beyond just managing updates, the sensor update policy houses this really critical self-defense mechanism. By default, it enables a feature called uninstall and maintenance protection. See, if an attacker manages to steal local administrator credentials on a workstation, their very first move is almost always to try and uninstall the security software so they can operate freely.
Right, they want to cut the alarm wires before they crack the safe.
Exactly. But with maintenance protection enabled, those stolen local admin credentials are just useless against the sensor. The attacker cannot uninstall, repair, or even pause the Falcon service through the Windows command line or the control panel. The system is locked at the kernel level.
Wow, so to get past it, you need a maintenance token. And looking at the mechanics here, this isn't just a static password an attacker could find saved in some IT wiki. It is a time-limited token.
Right, it's highly secure.
An authorized security administrator actually has to physically log into the cloud console, select that specific machine, and generate a temporary alphanumeric token. Then the tech at the keyboard has to input that token before the expiration window closes just to uninstall the agent.
It's a great defense. But that dependency on the cloud for authorization introduces a really fascinating engineering challenge regarding connectivity. Like, what happens when a host gets completely cut off from the internet?
Yeah.
If a laptop goes offline and loses communication with the CrowdStrike cloud for an extended period, typically 14 days, it enters reduced functionality mode, or RFM.
Wait, if a computer is offline, and can't communicate with the security team, why does the sensor drop into reduced functionality mode? Like, why not just continue aggressively blocking everything using the last known rule set? Isn't that safer?
It sounds safer, but it comes down to how deeply kernel-level security software integrates with the operating system itself. The Falcon sensor lives in Ring 0, the most privileged level of the OS.
Okay.
When Microsoft or Apple push an update to their operating systems, the actual memory structures change. CrowdStrike continuously pushes lightweight updates called channel files to the sensor. These act as an instruction set so the sensor knows how to interpret the new OS behavior without crashing.
Ah, I get it. So if a user goes offline for 3 weeks, their local Windows operating system might download and install a Microsoft update over a hotel Wi-Fi network somewhere. But because the Falcon sensor hasn't connected to the CrowdStrike cloud, it never received the updated channel file.
Exactly. The sensor wakes up, looks at the new Windows operating system behavior, and just doesn't recognize it. It might interpret a core Windows process as suspicious, or it might just become wildly unstable because the memory addresses it expects have moved.
So if the sensor simply tried to enforce its outdated rules, it would likely cause a total system crash, a blue screen of death.
Exactly. To prevent taking the machine down entirely, it intentionally drops into reduced functionality mode. It scales back its resource consumption and its aggressive blocking to ensure the host operating system remains stable. It chooses keeping the user's computer running over enforcing outdated kernel hooks.
That makes total sense. And admins can easily track these disconnected machines by filtering their XDR console with the query status, .rfm, right?
Yes, it acts as a clear signal to the IT team that a specific machine needs to be reconnected to the corporate network to pull down fresh channel files.
Okay, so we have deployed the sensors silently, we've intelligently routed them into groups using FQL, we've staggered our updates using N1 policies to ensure stability, and we've locked the sensors down with maintenance tokens.
A lot of prep work.
Exactly, it's all preparation. What happens when the system actually detects a threat? This is where the management tools hand the baton to the SOC, the Security Operations Center.
Because modern cyber warfare moves way too fast for manual intervention. When a ransomware payload executes, you cannot wait for a human analyst to finish their coffee, read an alert dashboard, and manually click a button to isolate the machine. You need instantaneous orchestration.
And the sources outline a powerful automation engine for this called Falcon Fusion SOR. SOR stands for Security Orchestration, Automation, and Response, and the entire workflow operates on a rigid trigger condition action model.
Right. So a trigger is the inciting event. For example, the sensor detects a high-severity indicator of attack, like a PowerShell script attempting to encrypt local files.
And the moment that trigger fires, the SO workflow moves to the condition. This is where the host groups we built earlier become totally vital.
Yes, exactly.
The workflow asks the cloud, we have a critical detection, but what kind of machine is this? Is it tagged as a standard workstation or is it a mission-critical database?
And the action executed depends entirely on that condition. If the tag confirms it as a standard workstation, the SOAR playbook might instantly execute a network containment action. It drops an impenetrable firewall around the endpoint, cutting it off from the entire corporate network and the internet, allowing communication only with the CrowdStrike cloud.
Wow.
Simultaneously, it automatically generates an incident ticket in ServiceNow and fires an alert into a dedicated SOC Slack channel.
So what does this all mean? Having Fusion SR configured is basically like having a digital bouncer at a club who operates at light speed. When a threat appears, the bouncer doesn't just kick them out. In the exact same millisecond, the bouncer checks their ID, throws them out the back door, files a police report, and texts the manager.
That is a perfect analogy, and the efficiency gains are massive. The source material notes that by leaning on these automated playbooks, managed security services like Falcon Complete are able to achieve a 1-minute mean time to contain, or MTTC.
Just 60 seconds.
60 seconds from the moment a threat executes to the moment the endpoint is completely isolated from the rest of the business.
A 1-minute NPPC is an incredible metric. But anyone who has worked in IT knows that automation can be double-edged. Like, security people are paranoid by nature. Doesn't giving a no-code automated workflow the power to unilaterally sever a server from the network completely terrify IT departments?
Oh, absolutely it does.
What if it makes a mistake? Couldn't a poorly written SOR playbook accidentally isolate the company's primary billing server right in the middle of a major financial quarter just because of a false positive?
That exact fear is why seasoned SOC teams utilize a crucial SR feature called Request for Human Input. You do not have to fully automate destructive actions.
You can build a checkpoint into the workflow.
Exactly. For high-impact actions like revoking a user's cloud identity and access management, or IAM role, or isolating a Tier 1 server, the Celor playbook pauses. It gathers all the forensic context, the command line arguments, the file paths, the user identity, and it presents a comprehensive package to a human analyst. The playbook will not proceed until the human clicks approve, decline, or escalate.
So the automation does all the heavy lifting of gathering the data, but the human retains the final authority on the big red button.
Yes. And if the analyst approves the containment, the investigation doesn't stop there. Because the machine is still communicating with the CrowdStrike cloud, the analyst can use a feature called real-time response, or RTR.
Right, RTR provides a secure, remote command line interface directly to the contained endpoint.
Which is huge.
Reading through the SOC workflows, analysts are running commands directly from their browsers to interrogate the isolated machine. They use getFile to silently pull a suspicious executable off the hard drive for sandbox analysis. They use killProcess to terminate active malware. They can even execute a memdump, pulling the machine's active system memory to see the exact encryption keys or passwords the attacker was attempting to use in real time.
It's incredible visibility. If we connect this to the bigger picture, we see a system designed not just to stop threats, but to make managing the defense mathematically scalable.
Right.
It starts with a silent, rebootless deployment via customer IDs. It intelligently routes hosts using kernel-level FQL tags to manage policy precedents. It cascades updates via the N1 crumple zone to ensure business stability. And finally, it empowers the SOC with Fusion SOR to bring threat containment down to mere seconds, while utilizing RTR to dissect the attack safely.
It really is a masterclass in logistical engineering. But as we wrap up, there is one highly specific detail hidden in the SOAR documentation that really reframes everything we've discussed today. And I want to leave you, the listener, with this thought.
Okay.
The architecture guides describe a scenario where SOAR is managing lateral movement, and it explicitly refers to identity as the new perimeter. It notes that a SOAR workflow can actually be configured to automatically enforce multi-factor authentication, or MFA, if a user profile on a security watch list attempts to pivot from a managed workstation to an unmanaged device.
Wow, yeah.
Think about the implications of that for a second. We just spent this entire deep dive mapping out how to lock down the physical hardware. We explored silent installations, rigorous host groups, mathematical policy precedents, maintenance tokens that legally bind the software to the kernel, and automated SR containment scripts that sever network cables in milliseconds.
Yeah, we focus entirely on the machine.
Exactly. But if the physical endpoint is now so highly automated, so deeply monitored, and so rigorously locked down by these platforms, is the actual battleground no longer the device itself? If the hardware is locked, is the true perimeter now just your human identity, the ghost in the machine typing on the keyboard? It is certainly something to mull over the next time you get a random MFA prompt on your phone.
That's a fascinating way to look at it.
Thank you so much for taking this deep dive with us. We'll catch you on the next one.